$3. That is the retail price today on any agricultural supply website or Amazon Marketplace for 1 square meter of polypropylene rational shade mesh. $3 that, positioned correctly on a fog-bearing coastal slope or mountain ridge, can intercept enough suspended atmospheric water to fill a family's daily drinking supply without a pipe, a pump, a filter subscription, or a bill. The mechanism requires no moving parts and no power source. Fog is not weather approaching. Fog is water already present in the air, suspended as liquid droplets between 1 and 100 micrometers in diameter. Those droplets are too light to fall on their own. What stops them is a surface. When a horizontal stream of fog-laden air encounters a mesh panel, the droplets collide with the fibers, coalesce into larger drops, grow heavy enough to fall, and run by gravity into a collection trough. A single square meter of mesh in a well-exposed site in a coastal fog zone produces between 3 and 10 liters of drinking quality water per day. A 10-meter panel produces between 30 and 100 liters. Every single day the fog arrives, which, in suitable coastal geographies, means the majority of mornings from late spring through early autumn. In 1994, atmospheric scientist Robert Schemenauer of the Atmospheric Environment Service of Canada and geographer Pilar Cereceda of the Pontificia Universidad Católica de Chile published the defining technical paper in the Journal of Applied Meteorology. The paper, titled A Proposed Standard Fog Collector for Use in High Elevation Regions, documented the design specifications, installation parameters, and measured yields of fog collectors deployed across sites in Chile, Ecuador, Eritrea, and Oman. It became the foundational engineering reference for every government program, NGO project, and academic study that followed. In 2012, Otto Klemm and colleagues at the University of Münster published a comprehensive global review in the journal AMBIO, cataloging fog harvesting systems across 4 continents, with measured daily yields ranging from 3 to 36 liters per square meter, depending on mesh porosity, site elevation, and local fog frequency. Neither paper is behind a paywall. Both are available through Google Scholar today. The global bottled water market was valued at $283 billion in 2022, according to Statista. The American Water Works Association reported that the average U.S. household water bill in 2023 ran between $70 and $83 per month. The American Society of Civil Engineers has valued the existing U.S. municipal water infrastructure asset base at over $1 trillion in their quadrennial infrastructure report. A passive collection system that requires no chemical treatment stage, no pumping energy, no distribution network, and no recurring consumable inputs is, from the perspective of that infrastructure economy, structurally inconvenient. Not because it threatens the entire system. Fog collection is geography-dependent and supplemental in most contexts, but because it generates no subscription, no meter reading, no treatment chemical sale, and no patent royalty. The polypropylene mesh that makes it work is an agricultural commodity, sold primarily to shade greenhouses. No company holds a licensing position on it. No marketing budget exists to explain that the same material collects water. That is not suppression. That is how product development investment gets allocated. The indigenous Guanche people of El Hierro, the westernmost island of the Canary Archipelago, built their entire water supply around a single tree. The tree stood on a ridge at approximately 900 meters elevation, precisely inside the northeast tradewind fog belt that bathes the island's upper slopes throughout the year. Its dense canopy of waxy laurel leaves condensed moisture from passing cloud and shed it continuously into stone cisterns at its base. Spanish colonial chroniclers documented the tree in detail in the 16th century. Its name was the garoe. Its species was Ocotea foetens, a laurisilva laurel native to Macaronesia. The chroniclers recorded that the garoe supplied sufficient water for the entire indigenous population of the island during the dry season months when no rain fell. When a storm felled the tree in 1610, the island's water security collapsed. The colonial administration spent decades attempting to find a hydraulic substitute using the engineering approaches they knew. The Guanche understanding of where on the ridge to site a fog collection surface, refined over centuries of direct observation, could not be replicated by engineers who arrived only after the tree was already gone. On the Pacific coast of South America, the Inca administration developed a parallel water technology that was not botanical, but topographic. The western Andean slopes between Lima and the Chilean border receive between 2 and 20 millimeters of annual rainfall. What they receive reliably from June through November is a dense fog bank called the Garua, driven inland off the cold Humboldt Current. The Garua sustains an ecosystem called lomas, cloud-dependent vegetation communities growing on otherwise hyper-arid desert slopes. The Inca road system in this zone included stone cisterns positioned at ridgelines where the Garua fog concentration was highest, at elevations corresponding to the upper boundary of the fog belt. Modern ecological studies of the Loma sites, including work published by researchers at the Universidad Nacional Agraria La Molina in Lima, have documented that the Garua delivers the hydraulic equivalent of between 100 and 400 millimeters of annual precipitation in the form of horizontal fog interception on vegetation surfaces. The Inca cistern positions on the ridgelines are not arbitrary. They are calibrated to the same fog belt geography that satellite fog frequency maps now confirm with MODIS atmospheric data. In Morocco's Anti-Atlas Mountains, at elevations between 1,000 and 1,800 meters above the Sousse Valley floor, Berber communities have used woven textile traps to intercept fog carried by Atlantic moisture flows penetrating the coastal ranges between November and March. French geographers documented the practice in regional surveys conducted in the early 20th century. In 2006, the Moroccan organization Dar Cimad began systematically scaling this traditional practice into an engineered installation using modern Rochelle mesh panels, eventually building what independent evaluators documented as the world's largest operational fog collection system, supplying water to over 400 people across 5 villages in the Ait Bamrain region. The project was funded in part by a USAID grant and was recognized by the United Nations Environment Program in its 2014 report on innovative water solutions in arid regions. The mesh panels came from a manufacturer, the knowledge of which specific ridges faced the right wind, at what season, at what elevation the cloud base sat, the knowledge that made the installation function, came from the communities whose grandparents had stretched woven cloth across the same ridgelines for generations. The Sabaean civilization of ancient Yemen, whose capital at Marib was one of the most hydraulically sophisticated urban centers of the ancient world, incorporated fog capture into the same water network that fed the Marib Dam. Inscriptions dating to approximately 700 BCE document the use of hillside cisterns on the windward faces of the Yemeni escarpment at elevations above 2,000 meters, designed to capture both seasonal rain and the persistent maritime fog ascending from the Gulf of Aden. The fog collection component of the Sabaean hydraulic system was documented in archaeological surveys conducted in the 1980s by Burkhard Vogt of the German Archaeological Institute. The Sabaean engineers did not separate fog collection from their larger water infrastructure. They understood it as part of a continuous atmospheric system and engineered for all of it at once. The Chilean government did not wait for private sector interest to validate the technology at operational scale. Beginning in the late 1980s, the Chilean Meteorological Service, in collaboration with the Universidad de Chile, deployed an array of 75 fog collectors, each measuring 48 square meters, at the coastal site of Chungungo in the Atacama Norte region. The installation was documented by Schemenauer and Cereceda in a 1992 paper in the journal Atmosphera, and again in their 1994 Journal of Applied Meteorology paper. Average daily yield from the 75-panel array was 11,000 liters, sufficient to supply the village of Chungungo's resident population of approximately 300 people. The water was gravity-fed from a ridgetop collection reservoir to a distribution tank at the village level. No pump, no treatment plant beyond a sediment filter at the tank inlet. The Chilean Ministry of Public Works issued a technical bulletin in 1993 classifying fog collection as a viable supplementary water source for coastal arid zones in the Atacama and Coquimbo regions. The U.S. Army Survival Manual, Field Manual FM 21-76, published by the Department of the Army, independently documents fog and dew collection on vegetation and surface condensation as standard field water procurement methods for personnel operating without resupply in fog-present terrain. A full reference covering the mesh specifications, frame dimensions, trough gradient calculations, orientation methodology by hemisphere, and the sediment filtration protocol that keeps collected water clean through a storage season is available in the description. Building a working collector requires 4 components. Racial shade mesh at 35 to 50% shade density is the correct specification. Higher shade density blocks airflow and reduces yield. Lower density reduces surface contact with fog droplets. The 35 to 50% range is the specification documented in the Schemenauer and Cereceda papers and confirmed in all subsequent field studies across 4 continents. Current price on Amazon and agricultural supply sites, $2 to $4 per square meter. 2 vertical support posts, wood or PVC pipe, each 2 meters tall. Nylon cord or stainless wire to tension the mesh tautly between the posts. A plastic rain gutter or a strip of corrugated polycarbonate folded into a V-channel as the collection trough. Total material cost for a 1 square meter test collector, $3 to $8. A 10 square meter panel producing meaningful daily water volume, $30 to $80, depending entirely on what you source locally. 3 siting decisions determine whether the collector produces water or stands empty. Orientation. The panel must face the direction from which fog approaches your location. For most Northern Hemisphere coastal sites, this means a northwest or west-facing installation. NASA's MODIS fog frequency data, freely accessible at worldview.earthdata.nasa.gov, shows fog occurrence frequency by month and elevation for any point on Earth at no cost. Elevation. You must be inside the fog belt, not below its base or above its ceiling. Observe where persistent morning cloud sits on nearby terrain through the cold months. That elevation is your target installation zone. Trough slope. The collection channel must run at a minimum 2-degree downward grade toward a single covered outlet feeding a closed storage container. Flat troughs lose collected water to evaporation within hours and develop algal growth within 2 weeks. The geometry is not complex. The siting is everything. A U.S. household paying $80 per month in water costs spends $960 per year. A family operating 5 10-square-meter fog collectors in a suitable coastal site at a one-time materials cost of between $150 and $400 recovers that capital expenditure in 3 to 5 months of avoided water bills. After that, the water costs nothing for the life of the mesh, which manufacturers rate at 7 to 10 years of outdoor exposure before porosity degradation begins to reduce yield. The Guanche people of El Hierro did not call it engineering. They called it the Garowe, and they built their island around it. The Inca engineers of coastal Peru did not publish in academic journals. They cut stone cisterns at the correct ridge elevations, and the Garua filled them every winter without assistance. The Berber communities of Morocco's anti-Atlas did not calculate mesh porosity coefficients. They stretched woven cloth across the ridges where the Atlantic fog arrived each November and collected what the cloth caught. The Sabaean civilization of ancient Yemen built the largest dam of the ancient world and understood that the fog condensing on the escarpment above it was part of the same hydraulic system they were managing below. Robert Schemenauer and Pilar Cereceda measured all of it, reduced it to engineering specifications, and published it in refereed international journals. The Chilean government built a working village water supply from it, using 75 panels and gravity alone. The mesh costs $3 per square meter. The fog arrives on its own schedule and has done so for longer than any of the civilizations mentioned here. If this is worth sharing, share it. Subscribe if you want to keep going in this direction.